right, welcome back to operating systems. So today we're talking about advanced scheduling. So we kind of alluded last time that we have different processes that we might care about, and if we want to schedule them specially, what can we do about it? Well, one thing we could do is just be super explicit about it. And we could just add priorities to our scheduling algorithm. So, since we may favor some, we'll just assign them a number. Who gets to decide the number? Well, we do, or we can let them decide themselves. Then we assign each process a priority, and the idea behind that is quite simple. If a process is a higher priority, we should run that first. And what we might do is just round robin processes of equal priority. This can be preemptive, non-preemptive. There's lots of choices we could make. We could round robin between different priorities if we really wanted to, if they're close enough. We could do all sorts of things. Whoops. So, if you're dealing with priorities, well, you need to assign a priority. Easiest thing to do is just assign a number to it and make the number have some type of meaning. So you can make a lower number mean higher priority or lower priority. It just depends on your tastes. So in Linux, one of its tastes is to make a lower number mean higher priority. So in Linux, when you see this, -20 means highest priority, and 19 is the lowest priority for normal processes. But if you just kind of implement a priority system, well, we go back to our old friend of starvation. So now you don't have any guarantees that starvation won't happen, because there could be a lot of high priority processes, and if there are so many high priority processes, you might never actually run a low priority process, and that way you would starve that low priority process. One solution, you could just make a band-aid to it immediately and just say, hey, well, if a low priority process hasn't run in a very long time, I'll just temporarily make it a higher priority until it runs, and then after it runs, I'll bump it back down to its original priority. So sure, you could do something like that. But now we have a new fun issue. So if you have priorities, an issue that might come up is something called priority inversion. And that means you accidentally make a low priority process behave like a high priority process. So we saw before that processes can depend on one another. So for example, when we had our sub process, well, our child process was doing a read, and it was waiting for our parent to do a write, and it couldn't progress until we did a write. So if you have a situation like that, then if who is doing the writing is a low priority process and who is doing the reading is a high priority process, well, you kind of inverted your priority for the low priority process, because if you want to free that bottleneck, you should at least temporarily make that low priority process a high priority process, because a high priority process depends on it. So one solution to this is something called priority inheritance. So if the kernel figures out that dependency, it will do exactly that. It will make that low priority process temporarily match the high priority process. And then after the dependency clears, it can go ahead and revert it back to a low priority process. And of course, with this, you may get chains of like process A depends on B, depends on C, depends on D. Well, in that case, the kernel would still have to detect it and do that priority inheritance for every single process in that chain, and then as soon as it's freed up, it can go ahead and revert them back to their normal priorities. So that's one thing you could do if you had priorities. We also kind of talked about that there's two types of processes, and they have different needs. So a foreground process can receive user input. Probably want good response time for that, because they're probably using a keyboard and a mouse and paying attention to it. While background processes, they probably don't need good response time. They're just running. You probably are concerned about throughput. You want to end the process as quickly as possible so you can get on to other things. So back in the day when terminals were real, like they were just an integrated keyboard and monitor, well, Unix was designed in such a way where it could tell if a process was connected to a terminal by a process group ID and its terminal ID. We don't actually have to know that for this course, but basically back in the day when things were much easier, you could tell whether or not a process was a foreground task or not because it had a terminal directly connected to it. So if that was the case, well, you could separate your processes out. Foreground processes need good response time, use round robin. Background processes just need throughput, do something simple like first come, first serve. If we had something like that, we now have the problem of we have to schedule between foreground and background processes. So if we have to schedule between foreground and background processes, well, you have to pick a scheduling algorithm to pick between them. So you could round robin between foreground and background if you want. You could favor foreground a bit more. Again, it is scheduling, so there is no correct answer, but that means you are round robining a round robining, which is lots of fun. So you could also make this more complicated. You could assign foreground processes as a higher priority than background. You could do whatever you want. It's scheduling. There is no one complete answer. It's just a series of trade-offs. So it's really complicated, and we haven't talked about having multiple cores yet. So far, we've only talked about having a single core. So we're going to assume an architecture called symmetric multiprocessing. What that means is all CPU cores are connected to the same memory. There's no performance difference or otherwise like addressing is different or anything like that. They're all connected to the same memory and are otherwise identical, except what is independent about each CPU core is its lowest level of cache. So like it's L0 or L1, that is independent to a CPU core, while between multiple CPU cores, they might share like an L2 or an L3 cache. So if we have multiple CPUs, we can just band-aid our solution, right? Just use the same scheduling algorithm, but it just now schedules between all CPUs. So it's the same idea, but it just makes more decisions. So while there is still an available CPU, it will just do the same scheduling decision and put that process that it picks on that CPU until all CPUs are full, and then it will just keep on doing that. So advantages to this, it definitely keeps all the CPUs busy because whenever one becomes idle, the scheduler would run and put a process on it. It's also fair to all processes as long as our scheduling algorithm is fair. Disadvantages of this is it's not scalable. So there is one scheduler and many CPU cores, and it has to coordinate and make a consistent decision for every CPU core. So it has to do it all. It can't do multiple CPU scheduling at once. So it has to just run the algorithm, say process 1 goes on this core, then process 2 goes on this core, then process 3 goes on this core. Because it wouldn't want to be in a situation where like you try and run the same process at 2 cores on the same time, it's just not going to work. So, and that's also a prelude to when we get into scheduling, or sorry, when we get into threads and actually have to deal with issues like that. The last disadvantage is poor cache locality. What does that mean? Cache locality just means things in the cache stick around, and if a process gets scheduled on the same CPU core, well, cache locality, if it's scheduled on the same CPU core, that means its cache might still be local on that same CPU and still might be around. So if you get context switched out and then context switched back onto the same CPU core, there might be some valid cache entries for your process still in the CPU, and you would hopefully get some better performance if you are scheduled on the same CPU. If your process runs on core 1, context switched out, and then context switched back onto core 2, then none of the caches are going to be valid for you, so you'll probably be a bit slower, and that's something you generally want to avoid. but this scheduling algorithm is what was used back in ye olden days, back in Linux 2.4. So you can figure out when that was released. It's probably like in the 90s or before, because no one had multiple cores. It just wasn't a thing. So they didn't really concern themselves about it too much. So when it started becoming more common, well, someone had the bright idea of saying, hey, we could create schedulers that are independent on each CPU core. So then we reduce our global decisions. We only have one big global decision we have to make, and that's when a new process gets created, what CPU core do we assign it to? So you assign it to the CPU core with the lowest number of processes currently on it. And that process will only stay on that CPU core and it will never move again. So some advantages of this is it's easy to implement. If I have one round robin queue, I can just make a round robin queue per CPU without really changing anything, and just picking what CPU to schedule a process on isn't that complicated. It's also scalable. We're not blocking on a global decision. Our global decision is just whenever a process is created, not coordinating whenever a CPU needs to context switch a process in and out. So each CPU core can be otherwise independent, and it can be really fast. And we also have good cache locality because processes never move between CPUs. So it will always, if its cache is still valid, it will be valid whenever it gets rerun on it. The disadvantages of this is there might be some load imbalance. So you can imagine, since we just make the decision at the beginning, we might be in a situation where we have, say we have 4 cores and 8 processes. So we assign 2 processes to each core. Well, we might get super unlucky and core 1 gets 2 really short processes and core 2 gets 2 really long processes. In that case, core 1 would finish, become idle, and then we can't do anything. So core 1 would just be idle, and then core 2 would just be ping-ponging back and forth between 2 processes. So we can do something better. So a compromise to that is, well, that seems like a ridiculous situation, and the solution should be fairly simple. So I can have a global scheduler that can rebalance the CPU cores. So if it notices that a CPU is idle, I can just take a process from one CPU to another, and that is called work stealing. So whenever this happens, that process that's switching CPU cores, well, it's going to have all its caches invalidated. If it's super performance sensitive, you probably don't want it to switch cores. So you might want some control over it, and that's what the term process affinity means. So it means the preference of a process to stay scheduled on the same core. So this is configurable, and you can do it even in Windows. So if you're in Windows and you're playing a game or something, and you want it to perform a little bit better, you can go into Task Manager, right-click it, and then go to Processor Affinity, set it to high, and that will mean it sticks around on the same core and won't switch, and you'll get a bit better performance. So you can do this for any process on your machine you care about performance on. So this work stealing version is basically the 01 scheduler from Linux 2.6. So fairly old, but this is basically how the scheduler worked in Linux. So another strategy, which also is related to high performance computing, is something called gang scheduling. Yes, I don't know why we have all these terrible terms. So what that means is basically multiple processes are scheduled as a group together, and the scheduler on each CPU cannot be completely independent because I need to schedule and context switch all these processes at the same time. So it's also called co-scheduling. And the idea behind this is if a bunch of processes are really dependent on each other, there's no use just running one and it's just going to be blocked immediately. I'll just schedule them all to run at the same time. And that way, If there's any dependencies, they're all running so they can resolve them. So this will be more of a thing if you are in high performance computing, and it's just another wrinkle in scheduling that you might have to consider depending on your application. So another problem is something called real-time scheduling. So real-time scheduling means there are some types of time constraints, either for a deadline or some type of rate. This is especially important in audio. So it's been a while since I took a signals class, but you know, audio is at a certain sample rate and there's a latency to process audio. Well, you want that to be as fast as possible so that your human brain doesn't see any delay or anything like that where the audio gets unsynced, and it has to keep up with that sampling rate and, you know, keep up with that sampling rate. Otherwise, you'll get like weird crackling or some other weird sounds, and it'll just sound like garbage. So it'll either sound like garbage, or if it's too slow, it'll be completely unsynchronized. Also, an extreme version of that, something like autopilot or like a missile or something like that, where if you're driving, you should probably react within a few milliseconds. Otherwise, you know, if there's a small child, like a real child, not a child process, you probably want to react pretty quickly, if you not to hit and kill them, not like our kill, like real kill, like bad kill. So probably want to react really quickly. If your autopilot takes a second to make a decision, then probably not a good thing. So there's two types of real time. One's hard real time, which is like you as a developer need to guarantee that something happens within a certain time limit. So for these systems, typically they're like embedded systems that are dead simple. Why are they dead simple? Because they have to be predictable. And if you're designing a system like this, well, guess what? When you compile your code, if you don't directly program in assembly, you're going to have to read assembly, count how many clock cycles each instruction takes, figure out the maximum number of instructions you need to accomplish your function or whatever you're trying to time, and then you have to guarantee that, hey, this will happen within a certain number of cycles, which corresponds to a certain number of seconds or microseconds or nanoseconds or whatever. So the system has to be dead simple. You have to count it. The other thing is a soft real-time system, and that basically you throw up your hands, you say it's too complicated to actually figure this out. But in practice, I always meet the deadline because my computer's just fast enough. So that's like your desktop system. It runs at scales of gigahertz, and it does lots of things very, very quickly. So audio would be like soft real time, and in practice, it always hits the deadline because your computer is just such overkill. But if you wanted to analyze the Linux kernel, there's no way you could make any guarantees whatsoever because, one, the actual scheduler is very complicated. Two, well, you don't know what's going on in the operating system at any given time. How long something takes to react depends on how many processes are running, depends on, you know, if the temperature, if you're throttling your CPU, it depends on like thousands and thousands of things, and you could never make any sort of guarantee. But you could just test it and say that, hey, it works, my users don't complain at me, it's good enough. So Linux can only do soft real time just because it's insanely complicated. So on the non-complicated side, when it does soft real time, it does very simple scheduling algorithms, and what we saw before are real scheduling algorithms that are used. So if you look at the Linux kernel source tree, you'll find first come, first serve. It's called skeg_FIFO, so anything that has to do with the scheduler in Linux is just called skeg. And you'll also find round robin. It's just called skeg_RR. So these things are actually used in the Linux kernel for any soft real time because you want that predictability, you want it to be really, really simple. So what it does, it has a multi-level queue for processes with the same priority, and the kernel will just dynamically adjust the priority if it finds that a real-time process hasn't run in a long time. And any of the soft real-time processes, it's always going to schedule the highest one first before running normal processes. And normal processes on Linux are what like 99% of the processes are going to be, and that defaults to the Linux scheduler, which, as we saw previously, could be that per core one. So, like I said, the real-time processes are always prioritized. They're soft real-time. They're either going to be first come, first serve, or round robin, and there's 100 static priority levels for this real-time. So they go from 0 to 99, where 0 means low priority and 99 means high priority. So the opposite of what I said at the beginning, which is really annoying. And the normal scheduling, so normal processes on Linux, which just use the normal scheduler, which you can see by schedule normal. By default, their priority is 0, and the priority ranges from -20 to 19, where a lower number means higher priority. And this number, for some reason, they call niceness, not to overload the term priority. So the idea behind that is if you are less nice, you have a lower number, you're greedier, you take more of the CPU. It's one way to think about it. So there is actually system calls for this, so you can change your niceness by using a system call called nice. So you could decide that your process is going to be less nice and therefore have a higher priority. So you could just set your own priority, and there's also like a set scheduler system call. So there's ways to interact with it with the kernel. So what does it look like with that mess? Well, Linux has a priority that tries to unify the real-time priority scale and its niceness into a Linux unified priority, which makes things real fun because trying to make it simpler, they just came up with a third priority. So here is our niceness that is fairly easy to figure out. So niceness varies from -20 to 19, and everything on this scale, anything to the left means it is high priority, and anything to the right means it's low priority. So for normal processes, -20 is towards the high priority side, and 19 is towards the low priority side. And they can range from -20 to 19. So the Linux priority tries to unify these two, like I said. So when it tries to unify them, its first goal is to make any normal process have a priority of 0 or above. So it will just scale the niceness by essentially adding 20 to it. So -20 becomes 0, 0 becomes 20, and 19 becomes 39. So it just scales it up. Then for real-time processes, and this is like a mutually exclusive thing, your process is either normal or it's real-time. It can't be both. So the Linux priority, it assigns numbers -1 to -100 to be real-time ones, which -100 being more high priority and -1 being less. So it has to take the soft real-time priority and essentially invert it. So a 0 becomes -1, and a 99 becomes -100. So why they do that, I don't know, but they do. So now we can actually read some more columns in HTOP. So when we had this, we kind of understand what PID is. We know what PID is, process ID, user. Now we can read the next two columns. So PRI is short for priority, and it is the Linux priority, these numbers at the bottom. So if it's negative, it's real time. If it's 0 or above, it's a normal process. So here I can see init, it has a priority of 20. And if it's a normal process, so it has a PRI of 0 or above, it means it has a niceness and it is valid. Otherwise, if it's a real time here and it's negative, niceness has absolutely no meaning. Why? I don't know. Don't ask me. I just work here. So we can see that init has a niceness of 0. It's just a normal process. Has a default priority. So we can look through these to see if we find anything interesting. So scroll down. Hey, there's something interesting. So there are some processes that have a priority of 9, which means they're still a normal process. And if we look at their niceness, it's -11. So they have a higher than normal priority. And what is this? It's wire plumber, pipe wire, and pipe wire pulse. Well, all those processes have to do with audio. So audio stuff generally has a higher priority because you want to hit those deadlines, right? So it doesn't ask for real time, it just asks for a bit of a higher priority. So we can scroll down, we can see this oddly named process, Tracker Miner FS3. Well, it has a priority of 39, niceness of 19, so it is a very low priority process. So whatever it does, we don't care about it very much. So we can explore some more. There's a -2. That's an interesting one. So it's a slightly higher priority, still a normal. Oh, it's -2, so it's of real-time priority. So it will be scheduled ahead of any other normal processes, and its niceness doesn't mean anything. So it's a fairly low priority real-time task, and it's called low memory monitor. So it's a process that just looks at your memory usage, and if it gets too scarily high, it probably just starts killing random processes. Well, probably not random. The kernel kills random processes. This is trying to probably be smarter than the kernel and kill a process that it thinks should go. So what else we got? So anything where the command is in green here means it is part of the kernel. So you can see the kernel, it has stuff that is less nice. So all these things that we don't know what they do, well, they seem to be fairly important. And we also see this one with a priority of RT. If the priority says RT, it means -100, which means absolutely highest priority real time, and it's something called migration. And guess what? If we look at all of them, there's 8 of them, and there is 1 for each of my CPU cores on my machine, and it's probably moving stuff around, and it is very important. So you can just explore, see what some tasks are. There's some other ones that seem to be less important. Hey, there's a watchdog that's real time. What the hell's a watchdog? I don't know. Well, actually I do, but what it is, not terribly important to you, but seems to be fairly important. And then that seems to be important. You know, you can have fun, you can explore. So we know what those 2 columns mean now. All right. So, the Linux scheduler evolution. So we saw the first 2, and now we are going to go to the present, which is called the completely fair scheduler. And the idea behind that is that, as the name would imply, it's fair. So if it's fair, it should also be responsive, have fairly good interactivity. So why don't we use the 01 scheduler? Well, it has a lot of issues with modern processes and desktop environments and how we use our machines now. So back in the day, foreground and background processes, that was a good division. It was easy to figure it out with a terminal attached to it, but now it is it's much less obvious. We have multiple monitors, we have multiple windows open. Just because we're not paying attention to a window or interacting with it does not mean it is not in the foreground, does not mean we are paying attention to it, and does not mean it is important. So like if you have a video, well, if you have a video playing in a window and you can see it, probably important. And then if you say, okay, well, I'll just figure out what's a foreground task. Obviously a video playing and you can see it, probably a foreground task. Well, if you do that, you just invent a bunch of heuristics. What's a heuristic? Just means it's a bunch of rules that are like an educated guess. And you could make other guesses, like if a process sleeps a lot waiting on a keyboard, maybe I'm interacting with it, maybe that means it's a foreground process, but it's ad hoc. What's ad hoc mean? That I just made up a bunch of stuff and it doesn't really have to be true. So if I am wrong with guessing and I guess that a foreground process is actually a background process, then suddenly your video starts lagging all the time and it's just a really bad experience, and generally the cost of being wrong is quite high and you don't really want to do something like that. So if I were to introduce fairness for different priority processes, I also have some different options I could do. I could use different time slices and still be kind of fair with round robin. I could, just assign a higher priority task, a bigger time slice, and then a less priority one, a lower priority one, a smaller time slice. I could do something like that, but then again, this could be ad hoc, could be unfair if I guess wrong. So, first we can talk about what is fair. So what is fair? Well, if we had infinitely small time slices, at any given point, if we have n processes, we would want to divide our CPU up so we give each process an nth of the CPU time. So that means if we have one process, we would give it our full undivided attention. If there are 3 processes running, we would give each a third of our time. So it's just divided equally among all current processes. What's that look like? Well, if we have process 1 that takes like 8 seconds to run, process 2 that takes 4, process 3 that takes 16, and process 4 that takes 4, we can assume that we have infinitely small time slices. We can context switch in 0 time. So we can divide our each column into 4 time slices just to make the numbers a bit better. So at the beginning, once we have all 4 processes, if we have 4 time units, if we were completely fair, we would give each process a single time unit. So each process would run for a single time unit, and each number here just represents how long that process has currently been running for. So after 4 time units, they all run for 1 time unit. Then for the next 4 time units, they all run for 1 time unit again. Again, we're being completely fair. Then this happens until a total of 16 time units pass, where each of our 4 processes was given a fourth of the CPU time. So each of them ran for 4 time units. So in that case, process 2 and process 4 are now complete. And if we were being completely fair, well, now there's 2 processes left. And if we have 4 time units to divide up, we would give each process 2 time units because there's only 2 left. So each of them would execute for 2 time units. So they'd go from 4 to 6. Then we would do it again for the next 4 time units. And then at time 24, process 1 is finally done. And we only have 1 process left. So we can dedicate all 4 time units to that 1 process and get it done. So process 3 would run for 4, then again for 4, and then at time 32, all the processes would be done, and throughout that, we were fair to them at all times. So, its name is ideal fair. Really fair, can't get more fair, but we made a very big assumption, which is not true, and that is that we have infinitely small time slices. Context switches do take time, and you can't just switch infinitely. So even though this is fair and each process gets the best response time, so the response time for this would be near 0 all the time because we have infinitely small time slices, in reality, it doesn't work like this. And also, we have to constantly scan all processes, which is ON, which is just really, really slow because context switching takes time, and also running the scheduling algorithm itself takes time, which is not running processes. So you want the scheduling algorithm itself to be as quick as possible. So that is where the completely fair scheduler comes into play. So what it does is for each runnable process, it assigns it a virtual runtime. In this case, virtual just means kind of fake. And whenever the scheduler needs to make a scheduling decision where a process runs for some time t, it will, whenever it's done running, it will record the virtual runtime and scale it by a weight based off the priority. So what does that mean? That means that if a process runs for like 1 second, if a process runs for, let's say, 2 seconds, then it could scale it by its weight, and say its weight was 0.5, then that means it would only get 1 second of virtual runtime and have that count against it less. So that is the intuition why Linux uses a lower number to mean lower, or a lower number to mean higher priority, because that priority is based off the weight. So a lower weight means your virtual runtime increases slower, and that counts against you less. So this virtual runtime will monotonically increase. What godforsaken math word does that mean? Well, that just means, monotonic just means it only increases, it never decreases. So we only add to that virtual runtime, we never subtract from it. So a scheduler in this case has a very easy decision. Its only decision is to pick the process with the lowest virtual runtime, because that needs to run more to get up to the fair amount. And the time slice it gets, the kernel will compute that time slice, which is t, based off what would be fair, based off how many processes are currently running and how far behind is this process to the next process's ideal, or the next process's runtime. So the scheduler will pick the t based off the ideal one, and then that scaling of that virtual runtime based off the weight is purely done from the priority. So this allows the process to run. When time slice ends, the scheduler just runs again. Or if it goes to sleep early or blocks for some reason, then only its runtime, how long it actually runs to, counts against it. It wouldn't use its full time slice, so it would only increase its virtual runtime by a little bit. So the completely fair scheduler implemented with red-black trees, yes, that thing you learned from algorithms that didn't actually have any practical application, has some practical application now. So red-black tree is a self-balancing binary search tree. And in this case, the keys that it is paying attention to is the virtual runtime. What does that mean? Well, it means all of our operations, like inserting, deleting, updating, and finding the minimum, are all O log n, which is quite fast. So whenever you create a process, or whenever you recompute its virtual runtime, well, you have to re-add it back to the tree, right? So you can see its decision, and all of this nice and fast. So in the implementation, the red-black tree, that virtual runtime is accounted for in nanosecond granularity, which is really, really fast. So if you haven't seen a nanosecond before, a nanosecond is about like that. This is how fast a nanosecond is if you consider the speed of light. So this is how much a nanosecond is going the speed of light. Pretty small, it's like 30 centimeters. So nanosecond, pretty fast. Speed of light, pretty quick. So that's really quick. And yeah, your CPUs operate on that, so that's actually not that long, so it actually matters how long your wires are in some cases, so that's why. So the nice thing about the completely fair scheduler 2 is that it favors I/O-bound processes by default. What does that mean? Well, that means if a process is I/O-bound, you're probably interacting with it because it's requesting some information from the kernel. It's waiting for some keyboard press or something like that. So it would not use all of its time slice, so its virtual runtime would only go up by a little bit, and then your kernel is going to run other processes. They're going to increase their virtual runtime more, and then when your process is finally gets the information it needs and unblocks, well, it's much more likely to run because it would likely have the lowest virtual runtime. So it would get scheduled to run pretty much immediately, get a good response time, then go back to sleep, probably still be the lowest one, and then its time slices would also get bigger and bigger. So if it needed to do a lot of computation after a bunch of input, it could. So with that, scheduling, even more complicated. It's like that fun thing, more money, more problems. Same thing with scheduling. More things, more features you add, more problems you get. So if you introduce priorities, guess what? Your problem is now priority inversion. You have to handle it. One way to handle it is through priority inheritance. You might also, have some processes that need good interactivity, others not so much, and you might try and discern which one is which. Well, if you make a bad decision on that, you will get really bad scheduling and probably make your users very unhappy. If you have multiple cores, well then they probably need something like per CPU queues. Then also I might have like real time, and if I have real time, I need things to be predictable. And then I can't make something very complicated that is very smart. If I try to throw AI at it, that just wouldn't work or something like that. Then we saw what is actually currently used in the Linux kernel today, and that's the completely fair scheduler that tries to model ideal fairness. So we get to end a bit early. This class will become ahead of the other classes, so they're not having a lecture tomorrow, so you will be a lecture ahead of them until Thanksgiving, and then everyone will be synchronized again. And also, we have a room for the midterm. Joy. When? November 15th. It's the Wednesday. So we have the room from 6 to 8. I was thinking of starting it at like 6:30 because it will be an hour and 15 minutes. Where? It is in the exam center, wherever that is. I have no idea where that is. One of you probably will. I will figure it out before then. If anyone has problems with it, let me know. Hopefully it's okay. It has to be in the evening because your guys' schedule is a complete mess, which puts me home at like 2 a.m., so thanks for that. But yeah, so that'll be fun. Let me know about it, and otherwise we get to end early. Yay! So just remember, pulling for you. We're all in this together.